A while back, I had two big questions about color. The first was, what are the primary colors and why are they what they are? Like, I'd been taught in elementary school that red, yellow, and blue are the three primary colors, but my computer screen uses red, green, and blue, and my printer uses magenta, yellow, and cyan. The second question was, why do different colors appear brighter than others, and in particular, why does yellow look so bright? I started thinking about this when I noticed that when I set my computer screen to black and white, changing the hue of a color in my drawing program still changed how bright it appeared, even though I wasn't touching the brightness slider. That made me realize that something weird must be going on. So I read a bunch from this book, and a bit from this website, and a ton from this website, and here's what I learned. First, let's go over some basics that'll probably be review for a lot of you, starting with light. Light is a wave. It's also a particle, but for now let's focus on how it's a wave. Waves have a length, called a wavelength, and light that we can see has a wavelength between 400 and 700 nanometers, which is smaller than a bacteria but bigger than a virus. If its wavelength is outside that range, it's still technically light, but we can't see it anymore, so we usually call it something else. Like if it's smaller than an atom, that's a gamma ray, and if it's longer than a couple of feet, that's a radio wave. We have, in our eyes, 4 types of cells that help us see. The first are called rods. They work better in really dim light, they're pretty good at noticing motion, and they contribute a lot to peripheral vision, but they don't help us see color that much, so we're not going to talk about them much today. The other 3 are all types of cone cells, and they're called S cones, M cones, and L cones, because they're really good at detecting light with really short, medium, and long wavelengths, respectively. So if some light enters our eye and it has a wavelength of 630 nanometers, that's on the long end of the range we can see, so it's going to activate the L cones a lot more than the M or S cones. The L cones are then going to pass that signal along to the brain, and you're going to have the experience of seeing something red. Now, how much each cell is activated depends on 2 things: how much light is hitting it and what the wavelength of that light is. Each type of cone cell has an ideal wavelength of light that activates it more than any other wavelength. For S cones, it's about 445 nanometers, for M cones, it's about 540, and for L cones, it's about 565. But all 3 of them are activated by light with wavelengths different from that. They're just not activated as much, and so they don't send as strong a signal to the brain. To put it another way, you can activate an M cone with 565 nanometer light, but you just need more light to activate it the same amount than if you were doing it with 540 nanometer light. So, if you were to emit some light into someone's eye and slowly decrease that light's wavelength from long to short, while keeping the amount of light the same, and while measuring how much each of the 3 types of cells are being activated, you would get something like these 3 overlapping bell curves. This graph represents how much each cell in your eye is activated by different possible wavelengths. For instance, light with a wavelength of 500 nanometers activates the S cones a little, the L cones a moderate amount, and the M cones a little more than the L cones. Now, here's the thing. There's almost never just one wavelength of light hitting an individual eye cell, and that means that there's a lot about the light hitting your eye that your eye won't be able to tell you about. For instance, a little bit of light from this frequency and a little bit of light from this frequency will look exactly the same as a lot of light from this frequency, because they'll both activate the L and M cones an equal amount and the S cones not at all. In fact, for any output that these 3 cells are giving you, there's basically an infinite number of combinations of wavelengths that might be causing it. So that covers the basics of what color is. Now let's talk about color mixing. You might have heard that there's 2 types of color mixing: additive mixing and subtractive mixing, but there's actually a third. Well, actually I read there are 6, but let's go over the first 3. Additive mixing is when you mix light directly. So like, if you take a red light and a green light and you shine them both at the same spot on a white wall, it'll probably look yellow. Predicting how this works is pretty straightforward. Like, if you mix 2 bunches of light, then you can basically just take how much one activates a given cell and add it to how much the other activates that cell, and you'll get how much the mixture will activate that cell. Do that for each of the 3 types of cells, and you get a more or less complete description of how your eye will react to that mixture. Pretty easy. Subtractive mixing is not so simple. See, when light hits an object, some of the light will get absorbed by the object, while some of it passes through it and some of it bounces off. Which of these happens depends both on the object and on the frequency of light. If the object absorbs all of the longer wavelengths, but the shorter ones bounce off, it'll look blue, and if it's the other way around, it'll look red. Air and water both let almost all of the light pass through, but a little bit of the shorter wavelengths bounce off, which is why if you have a little bit of them, they look clear, but if you try to look through miles of them, they start to look blue. Anyway, let's make a graph for a light filter based on what frequencies of light pass through it. The x-axis is the frequency of the light, and the y-axis is how much of that frequency passes through the filter. So the graph for a red filter might look something like this, mostly letting through long frequencies, while the graph for a blue filter might look something like this. Now, let's take a light filter that looks red because it only lets through these wavelengths, and another filter that looks yellow because it only lets through these wavelengths, and let's put one in front of the other. Only light that can pass through both of them will reach your eye, and as a result, it'll wind up looking kinda orange. But for another example, let's imagine 2 light filters that are a lot pickier. Let's imagine one that only lets through these frequencies and another that only lets through these frequencies. These would produce basically the same sensations in our eyes on their own, and yet when we put them on top of each other, it would look black because there aren't any frequencies that pass through both of them. If that seems weird, it's because I don't think there are actually any real-life substances that are quite that picky, but the point here is that the results of subtractive mixing can't be predicted just by how much the substances stimulate your eye on their own. You also need to know exactly how much the substances are absorbing each frequency of light. So I lost a bunch of footage from the middle of this video. I'm not sure how, but I have to re-record it now, so that's why my hair is going to be longer for the next couple minutes. So, now we come to the third type of color mixing, proportional mixing. Let's look at a wheel, half of which is painted red and half of which is painted blue. Let's also put up some graphs where this time the y-axis is the amount of light bouncing off of something rather than passing through it. The graph for the red half will look like this, and the graph for the blue half will look like this. When you spin the wheel super fast, light from the red half will hit your eye half the time, and light from the blue half will hit your eye the other half of the time. So to find out how much the light from the left half of the wheel is activating the cells in your eye, take how much it did when the wheel was still and divide it by 2. Do the same for the other half and then add the 2 and you get the total amount that the wheel is activating the cells in your eye. This is much more similar to additive mixing than subtractive mixing, with the big difference that instead of just adding together how much the two components are activating your eye, we're taking the average of the two. One major consequence of this is that with additive mixing, when you mix together red, green, and blue light, you get white, which is what happens when all 3 cells in your eye are activated a lot. If you do the same thing in subtractive mixing, who knows? Subtractive mixing is complicated, but you might get black, which is what happens when none of the cells in your eye are activated. And in proportional mixing, you get neutral gray, which is what happens when the 3 cells in your eye are all activated halfway. So, those are the 3 types of color mixing. But you might have noticed that I still haven't mentioned the main type of color mixing that most people have direct experience with. Mixing paint. The main reason for this is that mixing paint and mixing ink are both weird combinations of subtractive mixing and proportional mixing. If the individual pigment particles are mostly transparent, then light that hits the paint mixture will always pass through a whole bunch of both of the pigments. The pigments will act more or less like semi-transparent light filters, and it'll act more or less like subtractive mixing. But if the pigment particles aren't transparent, then by mixing red and yellow paint, all you're really doing is making a whole bunch of little tiny red and yellow dots, which is basically proportional mixing. Most paints are somewhere in between, but different paints will be at different points along this spectrum. So in order to predict exactly what color 2 paints are going to make together, you're going to need to know the exact spectral properties of both of the paints, which is to say how much each frequency of light bounces off of it, is absorbed by it, or passes through it, and you're going to need to know the typical size and transparency of each of the individual paint pigment particles. In the real world, artists don't actually bother, they just mix together 2 paints and see what happens. So, now let's talk about primary colors. The way I usually hear primary colors described is that they're a set of 3 colors, usually particular shades of red, green, and blue, and that by mixing them together in different proportions you can get any shade of any color you want. However, there isn't actually any set of colors that do that. It's gonna take a minute to prove why though, so let's get started. Let's make a graph of all of the possible reactions that your eye can have to a particular set of frequencies. There are 3 types of cells that each vary independently of each other, so this graph is going to need to be 3-dimensional, with each axis corresponding to a different cell. Actually, no, let's not do that. Firstly, because 3D graphs are hard to draw, and secondly, because we don't really need to. This stimulus is basically the same as this stimulus, but dimmer. So instead, let's imagine a graph of all of the possible ways our eye can be stimulated, where at least one type of cell is getting maxed out. The graph might look something like this. At each of the corners, only one type of cell is being activated, while in the middle, they're all being activated equally. If we do that experiment from earlier and shine a single frequency of light at your eye and slowly decrease the wavelength, the way your eye will react will make a path like this, with higher frequencies over here and lower frequencies over here. Now, if we mix together 2 frequencies of light using either proportional or additive mixing, the resulting sensation will be somewhere on a line between the 2, with where it is on the line depending on how much of each frequency we added to the combination. The only difference between the 2 is that in additive mixing, the result will be brighter than either of the 2, which again isn't represented on this graph. That means that if we have a set of colors we want to mix, the space of all of the colors we can make from those colors is the shape made by the points on this graph. Every actual stimulus of your eye is going to be the result of some combination of real-world frequencies, and since all of the actual frequencies fall on this line, that means that all of the sensations that ever actually happen are going to be somewhere in this shape. Sensations outside of that area are biologically possible, but there isn't actually any light that would cause our eye to do that. Now, if we want primary colors, we're going to need a set of points on this graph that make a shape that includes all of this shape, but is also inside that shape, which is impossible because the shape has curved edges. You would need an infinite number of points. Because of this, by our original definition of primary colors don't really exist. Although, for practical purposes, the space of real colors is roughly triangle-shaped, so you can get most of them with a red, a green, and a blue, which is why most computer screens are made up of tiny red, green, and blue lights. If you're using subtractive mixing, then all you need is one pigment that reflects red and green light but absorbs blue, one that reflects green and blue light but absorbs red, and one that reflects red and blue light but absorbs green. Those pigments on their own look yellow, cyan, and magenta respectively, which is what my printer uses, and by the rules of subtractive mixing, you should be able to get the same range of colors that red, green, and blue do by additive mixing. And now, with all of that background, we can finally answer one of the questions we started with at the beginning. Why did I learn in school that the three primary colors are red, yellow, and blue? Well, because, like I said, subtractive mixing is really stupidly complicated, and a couple hundred years ago when people came up with the red, yellow, blue system, we didn't have very good paint, so red, yellow, and blue happened to give people back then the largest range of colors of any set of 3 paints. To answer the second question, we're going to need to talk about something I haven't mentioned yet, the fact that although your eye first detects light with these 3 types of cells, that information goes through an initial layer of processing before the brain does anything else with it. The brain takes the 3 signals of how much are the L cones being activated, how much are the M cones being activated, and how much are the S cones being activated, which from now on let's call the red signal, the green signal, and the blue signal. The brain takes those and it converts them into a red versus green signal, a blue versus yellow signal, and a brightness signal. The red versus green signal is the simplest one, it's just the difference between the red and green signals. Interestingly, the brightness signal doesn't actually have anything to do with the blue signal, it's just the initial red plus the initial green signal. Finally, the last channel is basically the difference between the brightness channel and the blue channel. The brightness channel is red plus green, and when you have red plus green without any blue, you get yellow, so this is often called the yellow-blue channel. You could also describe the yellow-blue channel as red plus green minus blue. This fact, that the signal from our eye is immediately converted into this completely different system, explains a lot about how we subjectively perceive color. For instance, the idea of a reddish blue makes a lot more sense than the idea of a reddish green. That's because in this secondary system, redness varies independently from blueness, so it's pretty easy to imagine a bunch of both. But in this new system, green is the opposite of red, so in order to have more green, you need less red by definition. It also explains why yellow is the brightest color. Brightness is just the red input minus the green input, so as long as both red and green are maxed out, we're going to perceive the result as maximally bright. When there's a lot of blue with that red and green, then the yellow-blue axis is neutral and we perceive it as white. But when there isn't any blue to go with the red and green, then the blue-yellow axis is all the way in the yellow direction and we perceive it as yellow. So in this secondary system, yellow is equally as bright as white, it's just less blue. With that in mind, it now makes a lot more sense why yellow appears brighter than the other colors when my computer is set to black and white. My computer screen is doing its best to preserve how bright everything appears to be, but not necessarily how bright it actually is, while the brightness slider on my drawing program doesn't actually correspond to the same idea of brightness. I'm pretty sure it's based on how bright the brightest of the 3 colors coming out of my screen is. And finally, the question in the title has been answered. Thank you if you stuck around for that whole thing, I hope you learned something. I know I did doing research for this video. Let me know if I got anything wrong in the comments.